For this quiz, we're looking at coordination chemistry, and we're going to look first at the following complex ion that has the formula that's shown here. And as we're breaking down one of these coordination compounds, for this problem, we're looking for coordination number, geometry, d-electron count, and these are just things that are good to write down or take a mental note of whenever you see any coordination compound. And so when we start looking at this, right, the first thing we want to remember is that we have this EN that's here. This stands for ethylene diamine and is a really common ligand that you're going to see for these coordination compounds. And the important thing to remember about this is that it is bidentate. And what does that mean? Well, it means that it makes two connections to the central atom. And so basically it's got two different lone pairs on it, and those two lone pairs are both going to attach to the central metal within this ion. And because of this, there are three ethylene diamines within the complex ion. That's the part that's in brackets. And therefore the coordination number is 6. And if we want to draw it out, it's going to look something like this. So ethylene diamine is this structure. It has two amine groups, the NH2s shown here, or H2N, and it's connected by a small link of two carbons. And so each of those nitrogens contains a lone pair. Each of them is going to connect, and this is how we would demonstrate three ethylene diamines connecting to a central cobalt. The geometry, therefore, is going to be octahedral because we have 6 coordinations, and that is that octahedral geometry that we see for that coordination number of 6. And finally, we want to get the d-electron count. In this case, this is for cobalt of oxidation number 3. We know that cobalt is an oxidation number of 3 because the complex ion has a charge of 3. Ethylene diamine is neutral. Therefore, all that charge can be attributed to cobalt's oxidation number. And we know that the complex has a 3+ charge because it has 3 chlorides, Cl. We want to make sure we're recognizing the Cl, the 3 of them, the 3 Cls, on the outside as being chloride, Cl-. That's just anion cation, and when we have something like aluminum chloride, AlCl3, we know that the aluminum is 3+. That's the exact same principle that shows that this complex ion in the brackets is 3+. And knowing that, we get our D6 for cobalt. Okay, the next question is looking at another cobalt complex. This time we just have the ion, and it says that this complex ion appears orange. And we want to propose a color that another complex ion could be, where the only difference is that we've exchanged one of the cyanates for this carbon monoxide, the CO. And so in this case, right, what we want to note is that trading the cyanate for the carbonyl, the CO, means that we're getting a stronger ligand, and we have the spectrochemical ligand series provided here. And knowing what exactly this means is a really important part of understanding complex ions as well. What it shows is that the stronger the ligand is, the more destabilizing it's going to be for these d electrons. And so having a stronger ligand, right, the ligand strength is increasing. We're trading out the Cn- for the CO, means that the ligand strength increases, which means that the crystal field splitting is going to increase. And again, this is that difference in energy levels between 3 of the d orbitals that are not destabilized as much as 2 of them that are destabilized more. We'll show a picture of that in just a second. But this crystal field splitting is the difference within those d energy levels. That is going to get bigger because the ligand strength is getting larger, and therefore the energy of light that's absorbed, which promotes an electron from the low d energy levels to the high d energy levels, is going to go up as well. And so if the original complex appears orange, that means that it's absorbing something that's complementary to orange, maybe blue, right? Let's say it absorbs blue light. Now, when we have a stronger ligand, it's going to absorb higher energy than blue light. And therefore, that might be something like violet. And if it absorbs violet, it would appear yellow. Now, keep in mind that there's more than one correct answer to this. We're just proposing a color that it could be. And so if you say, well, I think that it might still absorb blue, right, just a higher frequency blue, that would be fine. So if you were to say that it absorbs higher frequency blue and I think it might still appear orange, that makes sense. But what wouldn't make sense is if you say, well, I think that it's going to absorb green light and therefore appear red. That wouldn't work because green light is lower energy than blue light and wouldn't follow the increased ligand strength that we're looking at here. Okay, Now we want to look at high spin versus low spin. We have two manganese complex ions, and we want to determine how many unpaired electrons are going to be in each of these. And so, when we're looking at unpaired electrons, we really need to know the D count. How many electrons are we even looking at in the first place? For both of these, manganese has an oxidation number of 2+, which means it's D5 for both. And we've determined, or it's given, that one is low spin while the other is high spin. And here are those two electron configurations. This is again showing the 5 different d orbitals as the blank spaces that the arrows sit in, and that crystal field splitting we talked about is the energy from one to the other. And in a low spin complex, the electrons would rather pair up, something they don't love to do. It's energetically unfavorable for them to pair, but they would rather pair than go to the higher energy level. And that's the case for the first low spin complex. The second complex is high spin, and in this case, the electrons would rather go to that higher energy level than pair with the original electrons. And so if we look at high spin and low spin, we can determine that for the low spin configuration, we have only one unpaired electron. And for the high spin, there are 5. Now, this question is a little bit in contrast to what you might see experimentally, where what you may determine is, well, it looks like there's no unpaired electrons, or there's very few unpaired electrons. That could lead to a determination about high spin versus low spin, which could lead to a conclusion about the crystal field splitting delta. Okay, the last question is about isomers. So remember that isomers are structures that have different connections of their atoms, right? The atoms that are here, we have them arranged in some different way. And so there are a few different types of isomers that we've studied as part of this course. And so I think the best way to approach this is just to start drawing things out. And so if we draw out just the complex ion, we might have these two structures. And these are actually different, right? We still have the iron at the center. We still have the same 6 ligands on each. But in this octahedral geometry, there's a difference in the left image where the cyanates are actually on opposite sides, whereas in the second image, the right image, they're adjacent to each other, right? Separated by only 90 degrees. And we call this first one the trans isomer and the second one a cis isomer. And this is the first type of isomerism that is definitely present in this structure. And we call this geometric isomerism. This is our cis-trans isomer, right? We have trans and we have cis. They are different structures, even though everything is still connected in the same way. Here's another structure that we could look at, right? So this is sort of analogous to the trans structure before, but now instead of writing CN for one of the cyanates, I've written NC. And what this shows is that the bond to the central metal is attaching to the nitrogen, not the carbon. And this is something that can be done with the cyanate ion specifically because it has multiple lone pairs. If we were to draw out its structure, we'll see that both nitrogen and carbon have lone pairs that they can use for bonding. And one of them is very likely favored compared to the other, right? The carbon is going to be doing the bonding in most cases, but there is the potential for this isomerism as well, where we have a certain ligand that uses a different lone pair to connect to the central metal. And this is a linkage isomer, and this is something that could be possible here as well through that cyanate ion. The third type is where we have a coordination isomer. And in this case, if we have the presence of a negatively charged ligand, it can swap with a negatively charged counterion. And in this case, we have the cyanate, we have the chloride. If those two switch, we still have the same atoms, the same chemical formula pretty much, but the bonding is different and we now have a coordination isomer. One thing to keep in mind is that we actually have different bonds set for these second two, and these are structural isomers, whereas the first one, we would call this a stereoisomer, where all the bonds are the same, it only has a difference in the arrangement of those bonds. There is no optical isomer or an enantiomer. That would be where we have our mirror image isomerization. That is not going to be relevant for this octahedral geometry where we only have 4 of one ligand and 2 of another.